Thermodynamics, Chapter 4, Lecture 2, Energy Balance for Closed Systems. Learning objective for Lecture 2 is to develop the general energy balance and apply it to closed systems. The reading assignment is Chapter 4, pages 168 to 174. One of the fundamental concepts in science, in physics, and in engineering is what's known as the conservation of energy. This conservation of energy is applied specifically to thermodynamics and what we call the First Law of Thermodynamics. It says the energy difference between the energy coming into a system minus the difference of the energy coming out of the system is equal to the change in energy of the system. So how can we, this is expressed in an equation very simply as En minus E out is delta E of the system. So energy in minus energy out, that can be things like heat, that can be work done on the system or work done by the system. The right-hand side, the change in energy of the system, is reflected in basically three concepts. It's internal energy, kinetic energy, or potential energy. There are some other ones, but the ones we'll primarily deal with are internal energy, kinetic energy, and potential energy. In this specific chapter, we're going to restrict ourselves to what's known as closed systems. This means that no mass crosses the system boundary. It's isolated. The book goes through and derives two fundamental equations. The most general case is shown here. Q is heat minus work equals change in internal energy, which is represented by U, plus change in kinetic energy, plus change in potential energy. The work can be boundary work, which we talked about in the last lecture, or it can be other kind of work we'll touch on in this specific lecture. You take this general case and you keep, if you apply a constant pressure, for example, if a process occurs under constant pressure, you can simplify this equation a lot because you can take the boundary work and the internal energy and combine them together in what's known as the enthalpy, and that's represented by this capital H. So in that case, only at constant pressure, so be very careful in these kind of problems and make sure it says constant pressure if you're going to use this equation here. Notice it looks very similar to the other one, but here we've basically taken part of the work and the change in internal energy and represented it by delta H, the enthalpy. Now the enthalpy you can get right from the tables, as we'll show in an example. So let's take a look at example 4-5. A piston cylinder device contains 25 grams of saturated water vapor that is maintained at constant pressure of 300 kilopascals. A resistance heater within the cylinder is turned on and passes a current of 0.2 amps for 5 minutes from a 120 volt source. At the same time, a heat loss of 3.7 kilojoules occurs. Determine the final temperature of the steam. So first of all, we got several things going on. We're given the mass. Also note it says at a constant pressure. So we're going to use that second formula because we can. It's at a constant pressure. We're also told that there's a energy input to the system because you have current being applied. So we know that if you run current through a wire, you develop a voltage. So therefore, you can impart energy. This is a heater. You also are told that there's heat going out of the system. So this shows a graph of what it looks like. Of course, we don't really know where 0.2 is yet, but we'll find that out in the answer. But I want to show you what it looks like here. It does say also, specifically, it's a saturated water vapor. So that's how we know it's right at 0.1, right? Remember that from chapter 2, that the PV diagram, this point is the saturated vapor state. Same as for a temperature versus specific volume, right? This point is exactly the point at which you have it's still water vapor here. It's basically 100% water vapor here, right? So again, be very careful when you read these problems. Pick out. That's why back in that particular chapter, I was stressed specifically to pay attention to the words. If it says saturated water vapor, you got to relate that to where it is on the diagram. If If it says, saturated water, it's all water, well, maybe it's over here, right? At the VF point rather than the VG point. If it's somewhere in between, if it's a liquid vapor mixture, well, then you know it's somewhere in between here and it has a quality. So again, you got to really pay attention to the wording in the problems. So since this is at a constant pressure, we're going to use the second formula. Also, we're not told anything about changing the kinetic energy, changing potential energy. In these specific problems, this sample he showed us isn't moving, and it isn't changing position. So therefore, these terms are going to be zero. So all we're left with is this term here. Now, the work other, that's the work into the system provided by the electric wire. So work is equal to voltage times current times change in temperature. So V is 120 volts. The current draw is 0.2 amps. The time difference is 300 seconds. So here we can multiply these out. We can convert to kilojoules. Remember, because that's our chosen unit in thermodynamics. It's not the joule, it's the kilojoule. So now we calculate what the work in is. We could go to the tables for state 1, which is 300 kilopascals, saturated vapor. So we can look up what the enthalpy is. It's the Hg value in the tables at 300 kilopascals. So make sure you can get this value. Go look it up in the table. 2,724.9 kilojoules per kilogram. So now we can determine the final state by using the first law. Wn minus Q out is equal to delta H. Remember, H is the capital H is the enthalpy, which is equal to M times delta H. And delta H is what we can get from the tables. This is the enthalpy per unit mass. So we can plug in the values we know. We know what work in is 7.2 kilojoules. The Q out, we're told, is 3.7 kilojoules. M is 0.025 kilograms. We're told that. Remember, it's grams. We got to convert to kilograms. Delta H is H2, which is the final, minus whatever the initial H was, which we're told, so we can actually calculate H2. We can simply solve this equation for H2. We get 2,864.9 kilojoules per kilogram. Now, so how do we know what the final state is? Well, again, we have to go into the tables. We know what the final pressure is. We know what the final enthalpy is per unit mass. So go into the table. So here we look into the tables. First of all, let's go to table A5, because again, we have no idea what state this is in. So if we look up table A5, I've made I just clipped a part of it, but go to the actual table and look yourself. You'll find an entry for the pressure of 300 kilopascals. So we come over to the enthalpy column, which is here, right? Here's HF, 561.43. Well, we're bigger than that. We're at 2,864. The Hg value is 2,724.9. We're even bigger than that. So in this case, H is greater than Hg. So what does that tell us? Well, it tells us we're superheated. And again, the only way we would know that is by going to table A5 first. So we can't use the values here. We have to go to this superheated table, and here we can look up, 300 kilopascals is 0.3 megapascals. So table A6, I've clipped a part of the table here, but here we go. This is 0.3 megapascals or 300 kilopascals. So we look at the H values. So here we're between 200 and 150, right? Because at 150, so you read the temperature here, run all the way across, get in the right column for the pressure, 2,761. We're bigger than that. So you go to the next one, 200 degrees C. Well, we're smaller than that. So we're somewhere between 150 and 200 degrees C. In this case, though, we're really close to the 200 degrees C. So the book just says it's 200 degrees C. It's actually 199 point something. But again, it's if it were somewhere, like say this was 2,800, it was really in between here. You couldn't just pick one of the closest. You're going to have to interpolate the values. So it's going to fall between 150 and 200 in that case. And so the only way to do that is just interpolate. You're given 2 points, 150 and this value, and 200 in that value. So you can just do a linear fit. Your calculators can do that for you. And I'm not going to spend time to show you how to work your calculator, but on your specific calculator, look it up in the manual, look it up online. Like TI-30 or TI, whatever you have, TI, whatever Texas Instruments or Casio calculator you have, you need to figure out how to interpolate on your calculator, because you'll have to do it on the exam. Let's take a look at example 4.6. A rigid tank is divided into 2 equal parts by a partition. Initially, one side of the tank contains 5 kilograms of water at 200 kilopascals and 25 degrees C, and the other side is evacuated. The partition is removed and the water expands into the entire tank. The water is allowed to exchange heat with its surroundings until the temperature in the tank returns to its initial value of 25 degrees C. Determine the volume of the tank, the final pressure, and the heat transfer for this process. So here, we're given the initial conditions shown here in blue. We really need to figure out exactly what our initial state is, though. And again, how we do that is we go to table either A4 or A5, depending on the information we're given. So here we're given the initial pressure and the initial temperature. So I'm going to go ahead and go to table A4 since I have the initial temperature. I look in the table, and at 25 degrees C, the saturation pressure is 3.1698 kilopascals. But our initial state, we're at 200 kilopascals. So we're way beyond the saturation pressure. So that tells me that our initial state is a compressed liquid. So since we're a compressed liquid, we're going to use the compressed liquid approximation when we can. So using that approximation, we can find the initial specific volume. It's this VF value at 25 degrees C, and you can read off the table, and you get approximately 0.001 cubic meters per kilogram. So therefore, the initial volume is given by the mass times the specific volume, 0.005 cubic meters. And since we're told the total volume of the tank doubles, then we also know the final volume of the tank, which is 2 times 0.005 cubic meters, so it's 0.01 cubic meters. So on to part B. At the final state, the specific volume of the water, how do we find that? Well, again, we just divide by the mass. We found what V2 is, 0.01 cubic meters divided by 0.5 kilograms, 0.002 cubic meters. So now what's our state? We don't really know. I mean, obviously, the PV diagram shows us what the answer is. We don't know 0.2 yet, so we don't know this down here yet. So how do we find out? Well, again, we go to the table A4. If you go to table A4 and you look up, you're at 25 degrees C. If you look at what VF value is and what the VG value is, you're right between those values. VF is 0.001, VG is 43.34. We're closer to the VF value than we are the VG value, but we're in between. So we are in the liquid vapor mixture region. That's where the final state is going to be. So we do know the final pressure, though, because if we're in this liquid vapor mixture region, this has a constant pressure in here. So again, you have to go back to the way and remember how the curves go. But the curves are actually, let's see if I can draw this for you. They're actually flat inside of here. At a given temperature, the curves are going to look something like this for the pressure versus specific volume, like something like that. So here they're flat in here. So what are they? They're exactly the saturation pressure for that temperature. So since we know we're at 25 degrees C, the final pressure is going to be the saturation pressure for 25 degrees C which again is right from the table, 3.1698 kilopascals. That's our final pressure. So the final part, part C, wants us to find how much heat is transferred to the system. So we're going to use the formula, Qn equals delta U. Uh, Again, the change in potential energy and the change in kinetic energy terms are both zero, so all we're left with is the delta U term. There's no work done on the system here or by the system since it's a rigid container. So what we need to find here, we know what the mass is. That's 5 kilograms. He told us that. We need to be able to find the internal energies per unit mass. So U1 we can find because we know what the state is. Again, we can use the approximation. It's a compressed liquid. So U1 is going to be approximately UF at 25 degrees C, which is in the table on the previous slide, so we can look that value up. U2, however, is a saturated liquid vapor mixture. I'm sorry, it's a liquid vapor mixture, so we have to calculate the quality. So the quality is the V value minus the VF divided by VFG. So V2 we know. We told it, again, we can calculate that. We calculated it from a couple slides ago. VF we can look up in the tables. VFG is the difference between VG and VF, so those are in the tables. So the quality is 2.3 times 10 to the minus fifth. So we can calculate what U2 is. U2 is UF, which we know. That's the 104.83 kilojoules per kilogram. The quality times UFG, which we look up in the table. So U2 we calculate 104.88 kilojoules per kilogram. So we can apply the formula. 5 kilograms times that difference in internal energy. Qn is 0.25 kilojoules. And notice this value is positive, which means that heat is transferred to the water.